Welcome everyone. So today I'm very happy to present to you the topic of my PhD thesis and the work of the last years. And the topic is hybrid imaging spectroscopy approaches for open pit mining, applications for virtual mine face geology. This PhD thesis was defended at the 4th of March 2021, and I'm just outlining it to load it up to YouTube for you. So I want to thank my supervisors, my referees, and the commission from last week. And this work was conducted at the University of Potsdam, the German Research Center for Geosciences, and the Geological Survey Department of the Republic of Cyprus. And it was submitted at the Faculty of Science at the University of Potsdam. So outlining roughly the next 30 minutes for you, we're starting with my motivation, going into the remote sensing principle introduction, as well as an introduction to materials and the area that I worked at. Then I'm going to give you a little overview about the mapping methods and the sensor complexity reduction that I tested and evaluated. And then I'm going to present to you my proposed and developed workflow for a mine face application. All of this is going to be completed by my outcomes and an outlook. So the material distribution within a mine face differs in the small scale, and false allocations need to be minimized to reduce material rehandling. I propose the use of superspectral mine face scanning to identify relevant materials and create distribution maps that allow for efficient material handling and also processing. I wanted to visualize this aim here by showing you the open cut mine face from the Apliki mine, which is a copper gold pyrite mine closed down in the 1970s. So here we mostly see secondary mineralization on the surface, but with hyperspectral we can identify 3 different areas in this mine face. One area is that material that would go to stockpiles here in purple and yellow. Another material would be the material that is going to the tailings here in green and red. And then we have material that is not itself high grade but can be used for high grading here in blue. So why am I proposing a new approach? Humanity struggles to achieve a balance between our material impact and the health of the planet. We're currently in an era of renewable energy, electrical vehicles, and we see more global economic growth, which means the demand for raw materials will rise in the future. In the case of copper, this means we already had a rise of 104% in the production of mined copper in the last 25 years. And the Copper Alliance projects an increase of another 50% in just the next 20 years. This shows that a sustainable approach to mining cannot only be achieved by the reduction of extraction alone, but it has to be built on developing technologies to create a safer, highly efficient extraction, sorting, and also recycling process. And for this, I propose the implementation of remote sensing into our mining workflow. So what do I mean by this? And this can be seen in different scales. We have satellite-based sensors that could be used for target identification from space, for exploration, for example. There could be active mining monitoring by UAV to increase and improve different mapping and modeling techniques. Then there's mine face scanning, which is in front of a mine or pit face in a higher resolution, identifying areas for extraction and for the different processing steps within the mine. And the last scale would be a sensor-based conveyor belt sorting, for example, or bulk sorting, or even an analysis of samples in very high resolution in the laboratory. And when I talk about remote sensing in the mining environment, in the context of this presentation, I'm talking about mine face scanning or pit face scanning. And in order to implement pit face scanning into the open pit, we still have a few challenges to overcome. First of all, we have the very harsh environment, which needs a rugged and easy to handle sensor. Handling means a decrease in size, weight, and also complexity. And then mining also poses the demand of a very high turnover rate, which means we have to speed up the data acquisition, processing, and mapping. For this, I propose the reduction of the sensor complexity to an optimum level. And optimum level here means this has to depend on the deposit, the complexity of the deposit, and the needed detail of material distinction. So how can I use, or how am I using spectroscopy for remote sensing? So when I talk about remote sensing, in this context I talk about solar optical reflectance spectroscopy. Spectroscopy describes the study of light as a function of wavelength, and the term reflectance spectrum refers to a plot of the intensity of reflection as a function of wavelength, like the plot that you can see here. A characteristic reflectance spectrum is caused by the absorption, transmission, or reflectance of incident light at a material surface, in our case a mineral surface. And minerals absorb photons by a variety of processes which are wavelength dependent. In my work I looked at the wavelength range of the visible to near infrared from 400 to 1000 nanometers and the shortwave infrared from 1000 to 2500 nanometers. And in this range, simplified here, a mineral can be identified by the position and the shape of its absorption features, and it can be semi-quantified by the depth of this feature, and this is shown schematically here. Unfortunately, not only the material influences its own absorption and reflectance spectrum, but other factors can influence the spectrum, and those are the particle size, the type of mineral mixture, the view geometry, the surface roughness, the surface coatings, and also the water content. And all of these can play a strong role in remote sensing as I aim for it, which means in an outdoor context of mine phase scanning. And that's why I want to introduce you to the different systems that are used in optical remote sensing. So just for context again, when I'm looking at a mine phase, I'm looking at it with a very specific aim, and that's the distinction between valuable and non-valuable material, or material that goes to tailings and material that goes to stockpiles. Excuse me. So there are basically three different categories of sensors, which is the hyperspectral, the superspectral, and the multispectral. Hyperspectral sensors, as you can see here in blue, collect the incident light in narrow consecutive overlapping bands and a large number of bands, up to 500 or more. This allows it to resolve very narrow absorption features, as you can see in the blue spectrum here, where we have these very narrow absorption features that are still visible. The other end of the spectrum of these sensors is the multispectral, which collects the images or the incoming signal in a small number of very specific wavelength ranges and bands, and these bands can be rather wide, as you can see here in the green spectrum. And the positioning of these bands depends also on the application of the sensor. So you can see the green spectrum below, that only larger bands are actually being resolved. Some intermediate is the superspectral range, and here you can see in orange the WorldView 3 satellite sensor band setting, and in black my proposed band setting. And superspectral imagery is a term loosely describing imagery that collects in between 15 and around 100 bands, but the incident light is also collected in a small number of specific wavelength ranges. These can either be also consecutive and overlapping, but wider, as for the black spectrum, or they can be positioned depending on the application. And you can see here in orange that even though we have a very few number of bands, only 16, still some of the smaller features in the veneer and also one smaller feature in the sphere can be resolved compared to the multispectral. So coming to my materials, I had 5 different data sets. The first laboratory data set was from Brazil, from different iron ore samples from 2 different mine sites in the Minas Gerais district, and this was used for my method development. Then I had 2 laboratory and 2 field data sets. 1 laboratory and 1 field data set was used for the workflow development from the Apliki mine in the Republic of Cyprus. And then the other data sets were from the Skouritissa 3 Hill deposit, an operating mine also in the Republic of Cyprus. Both of them are seen in the context of copper mining. For my iron ore samples, those are from 2 different mine sites in the Quadrilatero Ferry district. And here the supergene iron ores of the Minas Gerais district are divided into 3 categories: the enriched idabarite, the intermediate grade ore, and Kanga. All of these supergene iron ores result from the weathering of idabarite, and they degrade differently by undergoing this weathering under varying degrees of intensity. The expected iron carry here is hematite, magnetite, and martite, and amphiboles in the area are locally substituted by quartz. My samples had differing iron contents, but they were in the range of 24 to 68% of iron. For the Republic of Cyprus, just to give you the geological setting, the Cyprus sulfide deposit belonged to the mafic type of the volcanogenic massive sulfides, VMS, and here they are associated with the super subduction zone Forax setting of the Troodos ophiolite complex. Structurally, there are several asymmetrical north-northwest trending grabens, which are defined by sheeted dye complex domains. And these domains here correlate with the major sulfide mineralization. The deposits that I looked at here in the lower right corner is Apliki and the Three Hills deposit within Skouratissa, and both of those are located within the Solea Graben here in the west. The expected mineralization in the area is of pyrite, chalcopyrite, and sphalerite, with inclusions of galena and secondary copper-bearing minerals like chalcosite and covalite. And the alteration is dominated by silica and chlorite, which includes disseminated pyrite. We're having a closer look at the Apliki mine, which is a typical Cyprus-type VMS and an example of an oxidation zone overlaying a stockwork-type sulfide mineralization in chloride-bearing and silicified lava. All of this is hosted within the basaltic host lower pillow lava here. And in the case of Apliki, we're talking about a mineralization within a fault-bound zone of around 100 meters of width, which is surrounded here by the lower pillow lavas. Looking a bit closer into this open cut in the north, where I focused on, the reported grades here are reported between 1.6 to 3.5 weight % of copper, but the cupriferous massive sulfide ore has been mined out in the 1970s. Which means in this northern open cut, the prevailing alteration is chloritization, and this can spatially be classified into 3 subzones, which is smectidic, chloritic smectidic, and chloritic. In this chloritic centered zone, the magmatic minerals are absent and chlorite dominates. This only describes the stockwork mineralization here in the center, but it's surrounded to the west by massive gypsum veins in the silica-rich zone, and on top of this open cut is an oxidation zone. For my field data acquisition within Apliki mine, I used a tripod setting with a rotation head and the 2 high-spec sensors that were mounted on top of this tripod. Both of them are line scanners, a Veneer and a sphere scanner, collecting data in the range of 414 to 2498 nanometers. And in order to create an image with the line scanners, here there's a rotational movement of the head of this tripod stage. The positioning of the sensor depended on the accessibility and the safety of this open cut, which has been open and weathering since the 1970s. So the distance of the sensor to the mine face differed depending on this accessibility. And we had a distance from sensor to mine face of 50 to around 200 meters, which results in pixels that were collected at the mine face, representing areas between 3 to around 15 centimeters. In order to have a reflectance retrieval and correct the data for reflectance after the acquisition, white reflectance reference panels were placed in front of the mine face, here represented by these white dots. And 6 different panels were placed at the lowermost level, which was the only accessible level where we could actually reach. For the laboratory data acquisition, also the high-spec system was used, but it's mounted on top of a translation stage, which means the samples are moving underneath the sensor to create this image that is created line by line. the samples were left in their natural state to be comparable to the mine phase data. This means that we have weathered surfaces, fresh rock surfaces, we have soil-like components that are inhomogeneous, and we also had evaporites. For the geochemical data and validation, the Brazilian samples were already provided with the XRF results. For Apliki and Scurritissa, ICP, MS, carbon and sulfur analysis were done by the Bureau Veritas, and for Apliki, a qualitative mineralogy XRD was done at the University of Potsdam. Okay, so we're already coming to my evaluation of the mapping methods, and I wanted to introduce you to a very general workflow of how we are dealing with hyperspectral imagery, HSI. After the data acquisition, the data is processed prior to the analysis, which means a reflectance retrieval, a masking of low signal-to-noise ratio pixels, and it also can include a data dimensionality reduction. This is usually followed by a spectral library compilation or a feature extraction, and then the analysis, which can broadly be categorized into knowledge-based, data-driven, and hybrid. For the knowledge-based approach, this relies on the knowledge of the expected spectral behavior, whereas the data-driven approach relies on the data and reference data, either as training data or as end-member sets, which would be here the spectral library that we compiled. For this evaluation, I compared 20 different analysis approaches and 4 different spectral library compilation methods. And I want to just introduce you to the different accuracies of the mapping methods and to my main winners that I used for the further development. So for the hard classifier methods, I could plot the accuracy of the mapping versus the computation time of the mapping. Both will be very important for the results and how these results can be used within a mining context. Again, I talked about this high turnover rate, which means that the computation time is also essential in this context. For my hard classifier methods, I wanted to introduce you to the different categories of methods, but unfortunately the hybrid method here, the ENGeoMap, underperformed. That's why I'm just going to introduce you into a data-driven, comparison-based, learning-based, and also a knowledge-based approach. So the first data-driven comparison-based approach is the spectral angle mapper, which relies on the vectorization of pixel values and the comparison of the angle between those vectors of the sample and the end member. And this plots rather high in accuracy, but only of 66%, but it has a very high computation time, like a very fast computation time, sorry. The second method that I used was the data-driven training-based approach of support vector machines. This creates hyperplanes of the training samples and looks for the maximum margin between these hyperplanes as an indicator to find a decision boundary to distinguish the different training samples. A second data-driven comparison-based approach is the binary feature fitting, which relies on the triangulation of the spectrum and the comparison of the triangle parameters between my unknown pixel and the known end member sets. This plots a bit higher in accuracy as the SEM, even though it's the same method, but it has a higher computation time. And for my soft classifier methods, I used the minimum wavelength mapping, which is a knowledge-based feature modeling. And this looks for the position and feature depth, the minimum wavelength position and feature depth of a very specific absorption feature, and those are compared. And these are the 4 different methods that I used for my sensor complexity reduction to find out which sensor is optimal and which method is optimal. So for my robust sensor modeling, I used the approach of downsampling, which is an increase of bandwidth and a decrease of band number. Downsampling, or also smoothing, but in my case downsampling, will theoretically reduce the data size and the noise level, and it will make the data more manageable to implement in day-to-day activities. I'm using the downsampling here because my aim is to actually model a sensor that can be robust and used and built. So I'm talking about also reduction of complexity in terms of hardware components. and not collecting the full range of data and then downsampling it before an analysis. So I went through my data dimensionality reduction in 3 different steps. I did a systematic downsampling into 13 different sensors with bandwidths ranging from 1 nanometers to 100 nanometers. I did an exclusion of the atmospheric features in a very broad range of 1,300 to 2,010 nanometers, because here the spectrum is impacted by the atmospheric absorption features. As you can see here in gray, the atmospheric impact window. So distinct absorption features that stem from the minerals themselves will be masked in an outdoor setting, like my MindFace setting. And in a 3rd step, I downsampled to the Venier only data to check if the Venier is sufficient for mapping. So for my 1st step, for the systematic downsampling from 1 to 100 nanometers of bandwidth, I again plotted the accuracy against here the band number of the sensor, and you can see we're going from hyperspectral in the right to multispectral in the left. And for my SEM and my SVM analysis, you can see that the accuracy stays consistent with decreasing band numbers, or nearly consistent, only loses or wins even a few of percentages of accuracy. For my binary feature fitting, here actually with a decreasing band number, the accuracy increases. And in this comparison, this led me to the conclusion that a bandwidth of around 40 nanometers overall for my mapping approaches here could be sufficient for a good analysis. I also compared the minimum wavelength mapping for the sensors by looking at the double ALH feature, which is visible and detectable here around 2,200 nanometers. And you can see it has this very distinct double feature. And I checked by mapping this double feature over the decreasing band numbers to see up to which point these 2 features are actually still visible and can be distinguished. And this was only possible up to a downsampling of around 50 nanometers of bandwidth. So this leads me to the conclusion that by including broad features in the Venier and the medium and narrow features in the sphere, an ideal sensor would be around 40 nanometers in the Venier and 50 nanometers in the sphere region. So for my 2nd step, I excluded the varying atmosphere between 1,300 and 2,010 nanometers, and you can see this schematically on the graph on the left for my spectral library. And here the accuracy of mapping for BFF, SEM and SVM actually stays pretty consistent, which means that excluding the atmosphere does not have such a high influence on my mapping accuracies for these specific mapping approaches. For my 3rd data complexity reduction, I checked if Venier-only data could also be used to map and to distinguish the different materials here. And it shows that for the binary feature fitting, I actually have a loss of accuracy of around 4%, whereas the spectral angle mapper actually increases a couple of percent. I have to say, though, that this is possible for iron-rich materials, like my sample set from Brazil here, but it might not be viable and feasible for spectrally more diverse deposits. So that's why I went with my optimal sensor for my Apliki deposit, which is a copper deposit dominated by alteration mineralization. And this optimal sensor is of 40 nanometers in the Venier, 50 nanometers in the sphere, with the excluded atmosphere. Again, when we translate that into hardware, this means that the data size is reduced, the noise level will be reduced. We have data that is implementable into the day-to-day activities, and analytical features that would lie within this atmospheric impact window are not masked because we're excluding the whole area for our mapping. So we don't have false positives, for example. So this already brings me to my proposed workflow for MindFace mapping. So when you're actually in the lucky position of being in front of the MindFace with a hyperspectral sensor at hand, these are the 6 different steps that I would advise to follow. The first one is a very thorough field sampling and ground truthing, including a geochemical analysis. analysis. The second would be the HSI data acquisition and pre-processing and downsampling. The third is the spectral library compilation, followed by the comparison-based analysis. The fifth step would be a validation of the mapping based on different validation methods that could be accessible for the area that you're in. And if the maps that were created do not fit what we expect in this area, there would be an iteration with an optimization. And the sixth is the visualization of the results so that the on-site personnel can actually use the maps and the results for the planning ahead. So I'm going through these steps for the appliqué deposit now. I started with a sampling within spectrally homogeneous zones. These were predicted by Swear Radian's principal component analysis, and I sampled around 37 samples in these 15 different zones. This was followed by my HSI field data acquisition and the downsampling. I have to say here that the field data acquisition was done by an averaging of 10 different hyperspectral images. And the third step is already the spectral library compilation. I started this here with a geochemical clustering, an agglomerative bottom-up clustering of all of the geochemical results that I got from my sample set. And this results in these 7 different geochemical clusters. In order to compile a spectral library from this, I checked the spectra that are allocated within one geochemical cluster. And these spectra that were allocated within one cluster actually showed to be very comparable and had the same absorption features. So this also translated into 7 spectral clusters. And then I also checked the mineralogy of the different samples that were allocated within one geochemical and spectral cluster. And these also fitted these 7 different zonations that were found by the geochemical bottom-up clustering. So we have 7 different clusters that represent 7 different mineral zonations or geological zones here. The first cluster is the appliqué pillow-lavas. The second cluster is disseminated and weathered sulfide ore and sulfates. The third cluster are areas of higher silicification. The fourth cluster are veins of massive mineralization. The fifth cluster are the weathered pillow-lavas with a smectidic alteration. The sixth cluster is the chloritic stockwork, and the cluster 7 is my gypsum mineralization. So this spectral library was then used for the comparison-based mapping. And you can see the mapping results here of the binary feature fitting and the spectral angle mapper. Unfortunately, the support vector machines did not translate well into this outcrop and underperformed in the mapping. So that's why we're only comparing the BFF and the SEM here. And you can already see my first validation methods, which is by the different sampling points. And you can see the different sampling points within the image here, and those are already colored within their respective cluster colors. And I compared how well the 2 different mapping approaches actually mapped these different sampling points. And both for the SEM and the BFF, it showed that 18 out of 22 sample points could be identified. You can see this here with the yellow arrows, which sample points were actually classified incorrectly, and those differ for both methods. There's 2 more things that you can see in this specific mapping. First is that for the spectral angle mapper, we have more pixels that are classified as unclassifiable in black. And also SEM somehow is not able to classify cluster 2, which is the copper-rich sulfates, which have very high albedo here in my RGB imagery. And the second thing is that here you can see a high or large area of pixels that are classified as cluster 7 in pink, which is the gypsum mineralization, which we only expect in the north, in the west of the outcrop. So the gypsum here is overrepresented. This is also shown when we look at the second validation method, which is the expected zonation of the mine phase by Antivaches in 2015, which relied on a much larger sample set to find these different zonations here. And this shows that in the center of this mine phase, there is the expected chloritic zonation, which is phasing out into the smectidic-chloritic alteration towards the west and the east. And then this is surrounded by the appliqué pillow-lavas. And again, the gypsum alteration here is only expected to be dominant in the west of this outcrop. So this led me to an optimization iteration, and I checked my hyperspectral spectral library and the downsample spectral library, and wanted to see why gypsum is overrepresented. And it shows that the only spectral or the only absorption feature that distinguishes gypsum from the other sample sets here lies within this atmospheric absorption window. So it's marked here with the orange arrow. And in the downsampled data set, this absorption feature that distinguishes gypsum is not visible anymore, which means that the spectrum that I used to map or to compare to gypsum with my unknown pixels is actually not representative of gypsum. That's why I reduced the clusters to the 6 different clusters, and I've redone the BFF mapping here. And you can see that now this actually represents the outcrop very well, where we have our cluster of the chloridic stockwork in the center, and then the smectidic alteration towards the side, and all of this is hosted within the Appliqué pillow lava. And because I was happy with the result, now I used a 3D map to visualize this result and to also account for some of the distortions that can happen within a 2D imagery. And this kind of visualization can help people on site to actually identify the correct positioning of these different zonations. So, because I was happy with my result, I applied it to the Three Hills deposit within the operating copper gold pyrite mine Skouritissa. And to give you a very brief geological context here, so we have this open pit here where we have an east-west trending fault line which crosses right through the pit, and north of this fault line, from communication on site, we expect to have lower copper grades, whereas south of this fault line, we expect higher copper grades down into the pit bottom. And I had a very limited sampling set here of 15 different samples, and I broadly categorized them based on the geochemical analysis into samples with a higher copper content in pink, samples with a medium copper content in red, and samples with a very low copper content and clayish appearance in yellow. And when I use my approach to map this mine phase, it actually follows the expected zonation from the on-site geologists very well. So north of the fault line, we see the red pixels of a medium and lower copper content. South of the fault line, we see the higher copper content. And following this fault line actually is the area of very low copper content and clayish appearance here in yellow, which nearly paints the fault line for us. So yeah, this workflow applied to Three Hills actually works very well to show the geological setting here. This already brings me to my outcomes and main results. So first, I found that the reduction of the sensor complexity might actually improve the accuracy in the context of mining and in the context of distinguishing between broad material categories. Second, the sample selection has to be done by on-site experts for the spectral library generation. And third, the diffusion of the geological and the spectral expertise improves the accuracy and the mapping, what you could see in my example of the cluster reduction for Appliqué, for example. And fourth, with my site-specific hybrid workflow, it's actually possible to map mine phases under real conditions, which means using a less complex sensor to enable faster, easier, and more robust results without a loss of analysis or a maximum of 4% of accuracy here for using veneer only. That was the example. There are, of course, some open topics and further research to be done. First of all is the pre-processing. So how could the edge sensor and edge surface reflectance retrieval be improved to also account for different atmospheric changes? Second is to which degree is the deposit modeling influenced by possible image distortion? Third would be the site-specific spectral sampling. So can we have an optimum spectral sampling or spectral sampling frequency that could be automated for different geological applications or deposits, for example. And fourth is the data fusion. So how can different physics-based approaches be utilized to fuse the different geoscientific data sets to add value and to fuse low and high resolution geological methods, for example. So I want to just conclude for you. We started with the problem that hyperspectral systems for very narrow absorption feature detections in the lab are expensive, heavy, complex and delicate and might not be the best approach for an open pit mine phase mapping. And here experts are needed for handling, analysis and pre-processing. My suggested solution is an application-based sensor adaptation and analysis and a reduction of the sensor complexity by downsampling. And even though I use downsampling to prove this concept, I am aiming for an actual sensor complexity reduction in the hardware. So this has to be done by preserving the material-specific spectral characteristics, and this has to be evaluated throughout this downsampling process. And if the actual best-fitting sensor model still represents the complexity of the geological deposit that we have at hand. The outcomes of this approach for my examples from the Apliki copper mine and the Three Hills deposit were a reduced data size and also computation time without losing mapping accuracy, the possibility of deposit-specific complexities of the analysis, and highly precise mapping presented here as per pixel hard classifier maps. To conclude, in my thesis, I developed a general site-specific mine phase mapping approach. I did an in-depth evaluation of state-of-the-art mapping methods and sensor designs, and I showed an exemplary material mapping approach for copper mines. I started in my motivation by stating that the raw material demand is growing and it will grow in the future. And I'm very curious to see how the extraction of mining will adapt and if we actually have an increase of use of remote sensing technologies in mining. And with that, I thank you for your attention. And I just want to list different resources for you. So I'm leaving them up here for a few seconds that you can screenshot it and have a look at the different resources if you're interested. There's 2 more pages. And the last one. Thank you.